In the previous weeks, we started talking about the laws, the Newton's laws of viscosity. And we have looked at the first part of these laws. We checked some definitions, we explained some important terms. In the last lesson, we still looked at some important terms and we evaluated some calculations. I showed us how to deal with some analysis and understand the concepts behind viscosity and how it applies to real applications, the real living. Today we are going to solve a couple of questions, more examples for you. This time around, maybe more complex examples that would help us understand the concept of viscosity even further. So if you're just joining, I would encourage you to evaluate the previous lessons. There are about 2 or 3 lessons we've had before now. I want you to watch those lessons again and try to understand them. It will make it easier for you to understand this lesson. But if you want to watch these lessons first before you watch those, you can still do that. Okay? And if you're here, you have not subscribed to this channel, I want to encourage you to quickly subscribe now before you continue to watch this video. Now, at the same time, don't hesitate to give this video a thumbs up and let me know what you think about the lesson at the end of the lesson. All right, let's get started. A solid cylinder is sliding downward a pipe. As shown in the next slide, I'm going to show you the diagram soon. The cylinder is perfectly concentric with the center line of pipe with a film of oil between the cylinder and the surface. Okay, the first word you need to pay attention to is the word concentric. When something is concentric, it simply means that, for example, when you have 2 cylinders or 2 arcs or 2 circles, 2 or more cylinders, 2 or more arcs, 2 or more arcs that are concentric, it simply means they all have the same center. Okay, so if you have a cylinder and an arc that are concentric, it means they have the same center. If you have a cylinder and a circle that are concentric, it means they have the same center. And usually the bigger one surrounds the smaller one. The smaller circle is engulfed by the bigger circle of bigger cylinder or bigger arc. So what is presented in this question is that the cylinder is perfectly concentric with the center line of pipe with a film of oil between the cylinder and inside pipe surface. So we have been given the viscosity as 7 times 10 raised to the minus 3 kilogram per meters per second. We've also been given the length of the cylinder to be 15 millimeters. You know we can always convert millimeters to meters by dividing by 1000. Again, we have the diameter of the solid cylinder as 73.8 millimeters. This can also be converted to meters. And then we've also been given the diameter of the pipe as 74 millimeters. The diameter of the pipe will represent the outer diameter, while the diameter DI will represent the inner diameter. That's the diameter of the solid cylinder, because that is the cylinder inside the pipe. So that is why we are using DI, the inside diameter. And then the outside diameter, which will be the diameter of the pipe, the outer pipe, is 74 millimeters as given here. The mass of the solid cylinder is 2.5 kilogram. And the H, which represents the clearance between the solid cylinder and the pipe, is also given. Okay, if it's not given, we can always calculate it using this expression. And I'm going to show you how this expression is obtained, how they got this expression. You don't need to memorize it. You just need to know how it works. And then with or without it, you can always find your H if it is not given in the question and you have a question like this. So we will assume a linear velocity profile since the gap between pipe and solid cylinder H is very small. You will notice that we have the outer diameter as 74 millimeters, and then if you go up, you will notice that we have the inner diameter as 73.8. If we subtract 73.8 from 74, you would have about 0.2 or thereabout millimeters. If H is that small, then we can assume that we are dealing with a linear velocity profile. The question says find the downward velocity of the solid cylinder. In an attempt to find the downward velocity of the solid cylinder, I'm going to show you a couple of things that you can also evaluate and find and analyze from this particular question. There are some questions that may not bother to ask you to find the downward velocity of the cylinder. They might ask you to find some other things entirely. And some of those things we will need them to find the downward velocity. I'm going to show you how to find all of those things so that you can add them to your bank of knowledge. This is a diagram in question. This is a diagram we are dealing with. You can see we have a fixed pipe, that's the bigger pipe, and then we have a solid cylinder that is flowing downward or going downward in the big pipe. The bigger pipe is the fixed pipe with the outer diameter of d naught, and then the solid cylinder is a smaller cylinder that has the inner diameter of di. Okay, and then we have fluid, and then we have oil. We have oil inside the pipe, and then the cylinder is actually inside. All right, so you can also see that we have velocity profile here, right in here, and then you can see our H actually somewhere between the surface of the cylinder and the surface of the fixed pipe. This is our H right here, and then you can see that since the cylinder is going downward, the fluid, it simply means that the cylinder is going to have a weight called gravitational weight or gravitational force acting on it. That is why we have Fg here. And then this is pretty much most of the things we need to know, and we will then go ahead from here and begin our analysis. Again, let me tell you how we obtain this H now. Since these two surfaces are concentric, the cylinder is concentric with the pipe. It simply means that they have the same center. If they have the same center, that simply means if d naught is the diameter of the pipe, which is the bigger surface, it simply means the center can be somewhere in the middle here. If you pull from this center to the surface of the fixed pipe, that's going to be d naught over 2. That's going to be the radius, because from one side to the other side is d naught. So from the middle to one side would be d naught over 2, right? So that would be d naught over 2. Again, for the smaller surface, which is the solid cylinder, if you pull from that same middle, since they have the same middle, so you are picking the point from the same middle. So if you pick from the middle of this cylinder to the surface of the cylinder, you're going to have the radius as di over 2. Okay, the radius will be di over 2 because from one side the diameter is di from one side to the other. So from the center to one of the sides will be the radius, and that will be di, or ri will be equal to di over 2. That is inner radius. Okay, so from this point to this point is di over 2. From that same center to the outer center, it is d naught over 2. To find the H, which is between this side and this side, will just be the bigger radius minus the smaller radius will give us our H. So technically speaking, R naught minus Ri will be equal to our H. Our R naught will be equal to d naught over 2. Ri will be di over 2, and that's exactly how we would find this H. That's why you can see we have d naught over 2 minus di over 2 as our H somewhere here. Okay, so please pay attention to that understanding. It's very important. Now let's see what we can do with the values we have. We do know that there is a weight acting on the solid cylinder inside the fixed pipe. That weight will be given as W, which will be equal to mass of the cylinder multiplied by the acceleration of gravity on the cylinder. So that is why you can see we have weight equal to mg here. And you also know that our weight will be equal to specific weight multiplied by volume. We do know from the previous lessons that we dealt with that specific weight is equal to weight divided by volume. We do know that specific weight is going to be equal to weight divided by volume, And if you rearrange that, we can say weight is equal to specific weight multiplied by volume. We also know that specific weight is also equal to the mass density multiplied by acceleration due to gravity. We do know this too. So these are equations that we have dealt with before now, and they're going to come in handy in this particular question. We also mentioned earlier, so you just keep this somewhere. We keep this somewhere. We mentioned earlier that our h will be d naught minus di divided by 2. We know our d naught to be 0.074. It is actually 74 millimeters. If you convert that to meters, given us 73.8 millimeters in the question, all divided by 2 will give us 1 times 10 raised to the power minus 4 meters as our h. So we'll keep that somewhere too. We're going to need it very soon. Again, we had said that our shear stress is given as mu minus mu multiplied by dv dy for a linear velocity profile, because n is going to be equal to 1. This is going to be raised to power n. And for linear velocity profile, n is going to be equal to 1. So we have this here raised to power 1, and the 1 there is insignificant. That's why we have this here. And again, I mentioned to us in one of the lessons we had that the reason we do not use this minus in our calculation is because this minus indicates resistance to the flow. Okay, it represents resistance to the flow. When we have resistance to the flow, it simply means that we are talking about limit. Limit simply means as delta tends to 0 or as delta tends to a particular value. So because there is resistance, we're going to have the delta tending to a particular value. Okay, so when that happens and we replace this dv with delta, then we have delta v over delta y, delta v representing change in velocity, delta y representing our height. Okay, so when we have these as limits, it simply means that this negative sign is just going to disappear because we are not going to use it for our calculations anymore. So once you represent this with the delta sign, with the limit delta sign, and taking into account that we have some resistance because of the viscosity, so eventually this becomes shear stress equal to mu. Now the negative is not going to be there again because we're going to apply our mu now, and this time around it's going to be delta v over delta y, not just dv dy. It becomes delta v over delta y. Delta v will represent change in velocity. Okay, that means velocity of the solid cylinder minus velocity of the pipe. Velocity of the pipe will be equal to 0 because the pipe is fixed. So the pipe is fixed, its velocity is going to be equal to 0. And velocity of the solid cylinder will be the velocity at the top. So it's going to be v top or v solid cylinder minus v pipe. Where v pipe is 0, this is deleted, all divided by delta y, which is going to be our h. Okay, at the end of the day, we are left with shear stress equal to viscosity multiplied by velocity of the solid cylinder divided by h. Also, we have also talked about the fact that shear stress is equal to force over area. I remember mentioning to us that shear stress could also represent pressure, and pressure is force over area, but in this case it's going to be shear force divided by the area in question. Okay, so that is why we have our shear stress equal to force over area just at this particular point. All right, so we know that we are going to have weight on the, like I mentioned earlier, there is weight of gravity on the solid cylinder in the pipe. That weight could be represented as the force of gravity, and that will be equal to mg. The weight is also going to be equal to shear force, so both of them will be equal to mg. We do know that the mass of the solid cylinder, as given in the question, is 2.5, and we have our acceleration of gravity as 9.8. So if you multiply both of those out, you have your shear force as 24.5 newtons, or the weight acting on the solid cylinder as 24.5 newtons. So you keep that value somewhere. We're still going to use it. All right. So this is the cylinder, like I mentioned earlier, from the middle to the side of the cylinder inside, it's going to be Ri, and Ri will be equal to Di over 2. The area of a cylinder is usually given as 2 pi RL. That is the area of a cylinder, 2 pi RL. Okay? Our R is going to be equal to D over 2. So instead of writing R, we write D over 2. So if you write 2 pi D over 2 L, the 2 will cancel the 2 here. So you'll be left with just pi DL. Okay? And since we're dealing with the inner cylinder, you can see we still have our I, on the D here. So this becomes the contact area of the cylinder because we need the area. Okay, don't forget we had said that shear stress is equal to shear force over area. We found shear force, so we can easily find the area and then find our shear stress. All right, so if we continue this way, you'll find out that our area will be equal to pi multiplied by di. Di is 0.0738 as given in the question, multiplied by the length, which is 0.015. The length was given as 150 millimeters. If you convert that to meters, it gives us 0.015 meters. When you multiply all of these out, our pi is 22/7, it's a constant. Multiply all of these out, we would have 0.003477 squared meters. That would be the contact area for the cylinder, the solid cylinder. All right. So now that we have the contact area for the solid cylinder, we do know that our shear stress will be equal to shear force over area. We know that. The shear force, we calculated that to be 24.5 newtons. The area, we calculated that also to be 0.003477. You put those here, and that would be equal to, don't forget that we also said that our shear stress is equal to viscosity multiplied by the velocity of the cylinder divided by the height. Okay, and we do know that our viscosity was given in the question as 7 times 10 raised to the minus 3 kilogram per meters per second. We also know that our velocity of the cylinder was not given, and that is actually what we're looking for. Okay, and then we know that our height, we've calculated our height to be 1 times 10 raised to the minus 10. So Fs over A would be equal to 24.5 over 0.003477, and all of these here would be equal to everything that we have here, because this shear stress is stress. Okay, the two shear stresses are the same. So we enter the value of viscosity here, we enter the value of solid cylinder velocity, which we don't know, I'm looking for. We know the value of our h, we enter that here, and then the only thing missing here is velocity of the solid cylinder. When you rearrange these, you will find the value of velocity of the solid cylinder requested in the question to be equal to 10.1 meters per second. This example is actually a bit straightforward. However, I would recommend that you go over it 1 or 2 more times so that you can get all the necessary details to help you deal with this kind of problems in the future. All right, let us move to the next question. Power required to pull a horizontal plate is 6.4 watts. The plate has length of 50 centimeters and width of 20 centimeters. This plate is located at 0.5 millimeters over a fixed plate. So there are two plates. One plate is on top of another plate, and there is a gap of about 0.5 millimeters between them. The gap between the plates is filled with a liquid of viscosity 0.2 kilogram per meters per second. Find the necessary force exerted to pull the upper plate, and then find the velocity of the upper plate. Again, we are looking for velocity and then we are looking for force. And in finding velocity and force, there are a number of parameters that we would have to, first of all, determine. So let's get started. Let me point your attention to all the parameters given. in the question. We have our viscosity to be 0.2 kilogram per meters per second. We have power given as 6.4 watt. We have the plate has a length. We have the length of the plate as 50 centimeters. The width of the plate is 20 centimeters. That simply means with these two parameters, we can easily find the contact area of the plate with the liquid. And then we also have the height, the gap between the two plates, the fixed plate and the variable plate, 0.5 millimeters. That's the gap between them. We have that. Okay, some other factors not given here would be the acceleration due to gravity, which is 9.8 meters per second squared. We know that. And other things that we might want to use as we go on. All right, so let's get started. You can see we have a picture representation of the two plates. This is a fixed plate right at the bottom, and then this is the variable plate at the top with length 50 centimeters by 20 centimeters. There's a force F pulling it, and then there is a liquid between the two plates. Okay, we've been given the viscosity to be 0.2 kilogram per meters per second. So we have the area to be length times breadth, and that will be 50 times 20, and that will be 0.5 multiplied by 0.2. 0.5 is when you convert 50 centimeters to meters. You just divide this by 100. That gives us meters. And then divide 20 by 100. That gives us 0.2 meters. So when you multiply both of them together, it gives us 0.1 squared meters. So the contact area is 0.1 squared meters. And then we were given the power to be equal to 6.4 watt. I should quickly call your attention to the fact that power is usually equal to work done divided by time. Work done is equal to force times distance. So we can say that power is equal to force times distance over time. That's exactly what we have here. And again, we know that our distance over time is equal to velocity. So we can say that our power will be equal to force times velocity. So we can say that our power will therefore be equal to force times velocity. So that's why we have power equal to force times velocity, and velocity is equal to 6.4 watt. So F times V equal to 6.4 watt. Okay. So if we are looking for velocity, you can rearrange this equation to find, if we can find force, then we can find our velocity by just making V the subject of this formula, and then you can find your velocity. Or if we find velocity first, you can then find F by making F the subject of the formula. It then becomes 6.4 divided by V. All right, let's go ahead and see how the whole analysis would play out. Don't forget that we had said that the H is 0.5 millimeters as given in the question. You can easily convert that to meters. The gap between the two plates is H, as you can see. And then this is very small. This is very small. So we can assume that we're dealing with linear velocity profile. All right. You keep that in mind somewhere, and then let's go on. You will find out that right from the beginning, we had said that our shear stress is equal to minus mu multiplied by dv the y. Okay, and then when we bring in the limit to convert this to delta v over delta y, this negative disappears. So we have shear stress will be equal to mu without a negative. Now v top minus v bottom, that is velocity at the top of the plate minus velocity at the bottom of the plate divided by h, where velocity of the bottom of the plate will be equal to 0, so that disappears. And then our delta y will be equal to our h, which is the vertical height between the two plates. All right, so h is very small, and since h is very small, as delta y tends to 0, that means as h tends to 0 or as delta y tends to 0, we're going to introduce this limit, delta v over delta y, and then the negative is going to disappear. This negative is going to disappear. We're not going to use that. All right. Then once we have that, then we can easily say that since from the beginning we already said that our shear stress is also equal to shear force over area, and shear stress is also equal to mu, the velocity, multiplied by the velocity at the top of the plate divided by h, we can equate these two. Mu v top over h will be equal to fs over a, which is exactly what we do have here. Don't forget that we have already calculated our a, so we know our a. We also know our viscosity, so we know that. We'll put that here. We also know our h. We'll put value of our h here. The only thing we don't know is our v top and our fs. We don't know v, we don't know f. So this becomes an equation with two unknowns. We also have another equation here with two unknowns. So you can just solve these two equations simultaneously, and then you find the value of your V and then the value. The V we're looking for, this V top is the same thing as this V. This shear force Fs is the same thing as this force we have here. So you can solve these two equations simultaneously, and then you find the value of your force, the shear force, and then the value of your V, the velocity at the top. Okay, so let's go ahead and use substitution method in this case. Whatever method of simultaneous equation you want to use, you can use to solve these two equations to find the two unknowns. But whatever you do, make sure you do it correctly. We will make use of the substitution method to solve these two equations. All right, so we have F over 0.1, which is our area, would be equal to 0.2, which is our viscosity. And then we have our V top all divided by our H. Our H is 0.5 times 10 to the power minus 3 because we converted the millimeters to meters. We have this here. And then this is our V top. From this first equation, we can say our V will be equal to 6.4 over F. So instead of writing V here, we write 6.4 over F here. So that's why we have 0.2 multiplied by 6.4 over F multiplied by 1 over 0.5 times 10 to the power minus 3. Okay, if you solve these two equations, if you solve this equation by just cross multiplying, you have F squared will be equal to 0.2 multiplied by 6.4 by 0.1, then divided by this, and you find your shear force to be equal to 16 newtons. Okay, now that you know your shear force to be 16 newtons, you go back to equation 1, and then you say, okay, since F is equal to 16 newtons, and I know that our power P is equal to force times velocity, and we know power is equal to 6.4 watt as given in the question. So if we quickly substitute the value of 16 into that equation, we can say our V therefore will be equal to 6.4 over F, which is equal to 6.4 over 16, and that gives us 0.4 meters per second. So we have found the force, and then we have found the velocity as requested in the question given. Again, I would encourage you to go over this question one or two more times so that whatever is unclear to you can become clear. And if you do have any questions along the line, you do not hesitate to reach out to me and let me know exactly how I can assist in those areas. All right, let's take it a step further and try to solve one or two more problems. Here is another question. A rod 150 millimeter in diameter moves along its axis horizontally at 0.15 meters per second inside a concentric cylinder, which is 150.4 millimeters in diameter and 1.1 meter long. So what you can see here is that the word concentric has come up again. And we have a rod and a cylinder in this particular case. So the rod moves along its axis horizontally at a particular speed inside a cylinder. The space between them is filled with an oil of specific gravity of 0.82 and kinematic viscosity of 10 raised to the power minus 4 meters squared per second. What is the viscosity resisting this motion? So we're looking for the viscosity resisting this motion. Along the line, we would certainly have to find more than the viscosity. We will find the force, we'll find the viscosity, and a couple of other parameters along the line. So let's see exactly how this question can be dealt with. Before we go on, you might want to quickly look at this cylinder and the rod and how they are connected. You can see we have the big cylinder, which has diameter of D naught, and then we have the rod right in between the cylinder with the diameter of Di. And since they are concentric, it simply means both of them have the same center. Using the same analysis we used the other time, we can easily find our H, or we can easily create an expression between our H and the diameters. Our H will be equal to D naught minus Di over 2. Okay, and then again you can see we have every other parameters given, and then we have the oil right somewhere in the middle, and we have been told that this rod is moving horizontally. All right, so let us find the shear force with which the rod is moving, and then we're going to also find the force of resistance against the movement of the rod in the fluid. Okay, and as we go ahead to do that, we can find the shear stress if we need to find that and find every other parameter that is missing. All right, let's go ahead. Don't forget all the millimeters value will be converted to meters. We have 150.4 millimeters diameter that can be converted to meters by dividing that by 1000. We have another 150 millimeters right at the top there that can also be converted to meters by dividing it by 1000. By the way, 150.4 minus 150 will give us, as d naught minus di will give us 0.4. All divided by 2 will give us our h. 0.4 divided by 2 will then give us our h. Let's move on. You already know the formula for kinematic viscosity. We talked about that in the previous lesson. In one of the lessons we had, one of the two lessons we had previously before now. We also talked about the specific gravity of a particular material or substance and how it can be used. I'm going to show you how you can also use that formula right now. All right, let's begin. From the question, what you will find out is that we have our DI 150 millimeters, that gives us 0.15 meters. DO, D outer, is equal to 150.4 millimeters, that gives us 0.1504 meters. Specific gravity of oil is 0. Kinematic viscosity of oil is 10 raised to the power minus 4 meters squared per second. And then mass density of water is equal to 1000 kilogram per cubic meter. Okay, you know that density is equal to mass over volume. We all know that. We had mentioned earlier that density is equal to mass over volume. So the mass density of water is given as 1000 kilogram per cubic meters. This is a constant, by the way, for water. Okay, our v is constant, so it means that constant velocity. And if v is constant, it simply means our acceleration a would be equal to 0. So if acceleration is equal to 0, it simply means the net force would also be equal to 0, because force is equal to mass times acceleration, okay? And that will be equal to the mass of the rod multiplied by 0, and that gives us 0. The net force will be equal to 0. This simply means that the shear force will be equal to the force of resistance in the fluid, in the cylinder, okay? The force resisting the rod from moving forward horizontally in the cylinder is equal to the force trying to move the body forward. When those two forces are equal, it simply means velocity is constant and then there is no acceleration. Acceleration is equal to 0. All right, now that we understand all of these concepts, let's go ahead and apply them. So our h is equal to dO minus di over 2. That gives us 0.0002 meters. That is small, way small. That's about 2 times 10 raised to the power minus 4 meters. So this tells us that we are dealing with a linear velocity profile. Okay. Also, we know our tau, which is shear stress, is equal to minus viscosity, as you can see here, multiplied by dv the y. If we find the limit of delta y as delta y tends to 0, because h is very small, as delta y tends to 0, this becomes delta v divided by delta y, and then we have just the viscosity here without a negative sign, because we are considering the fact that there is a resistance, and that this negative just represents resistance. And then when we have delta, that shows that, okay, as h tends to 0, as the height becomes smaller and smaller, all right, this becomes delta v over delta y. The viscosity, negative sign becomes negligible, so we don't use it. So we know that our shear stress is equal to this, which is going to be equal to mu delta v over delta y. We also know that our shear stress, as discussed in previous studies, is the same thing as force over area, which is shear force over area. So we can equate both of them, and when we do that, we can rearrange this to find whatever is missing here. In this particular case, we do know that our delta v will be equal to v rod minus v cylinder, all divided by delta y, and delta y will be h, and this gives us Fs over A equal to viscosity multiplied by v rod over h. Okay, so we keep that somewhere because we're going to come back to it. Then we have the kinematic viscosity, of the material, which is usually equal to the absolute viscosity of the material divided by the mass density of the material. Okay, so this is the mass density of the material. This is the absolute density of the material. The material in question here is the oil. Okay, so we have the viscosity of oil divided by the mass density of oil, all equal to the kinematic viscosity of oil. If you rearrange these, we can say that our viscosity of oil will be equal to the kinematic viscosity of oil multiplied by the mass density of oil. So we have the kinematic viscosity of oil given as 10 raised to the power minus 4. If we scroll up, you know that the kinematic viscosity of oil is given as 10 raised to the power minus 4. So we can bring that right down into this equation. And then again, we have the mass density of oil. That is not given in the question, but we can always calculate it. We can always find it. We know that our specific gravity of a material is always equal to the mass density of that material divided by the mass density of water. Since we know the mass density of water to be 1000, we know the specific gravity to be 0.82. If we put those two in the equation, we can then easily find the mass density of our oil, which is just going to be equal to, when we cross multiply, from saying that the specific gravity of oil is equal to the mass density of oil over mass density of water. If we cross multiply, we can easily find the mass density of oil to be equal to the specific gravity of oil multiplied by the mass density of water. If we do that, we would obtain 820. So 820, you put that here, multiplied by 10 raised to the power minus 4 will give us 0.082. Will give us 0.082 kilogram per meter second. So this gives us the viscosity of the oil. Okay, now that we know the viscosity of the oil, we have been able to find another unknown in this equation. So we know our A, we know viscosity, we know H, and then we know the velocity of the rod in the question. The only thing we don't know in this equation is Fs. We can then go ahead and try to apply all the parameters to the equation. All right, let's take it a step further. So we can easily find the contact area. The contact area of the rod would be 2 pi RL. Our R will be equal to D over 2. So 2 will cancel 2, so we are left with pi DL. So the area, contact area of the rod with oil will be pi DL, which is exactly what we do have here, pi DL. Using that, it's going to be equal to 22 over 7 multiplied by the density of the rod multiplied by the length of the rod. If you do that, you will obtain 0.51836 as the contact area of the rod with oil. Okay, so you keep that somewhere, and then we do know our length is 1.1 meters, by the way. That's what we're going to use as the value of L here. We do know that our force will be equal to viscosity of oil multiplied by area multiplied by V rod over H. And that is from this particular equation here. Okay, we just cross multiply, and then F will be equal to A times viscosity times V rod over H. So since we know A from what we just calculated, we know the viscosity of oil, we calculated that. We also know the V rod given in the question, and then we know our H, which we already calculated too. If you put all of those values right in here, you will find the shear force or the resistive force as 31.88 newtons. This value, 31.88 newtons, represent the shear force and would also represent the resistive force. That marks the end of this particular question. We've been able to find all the parameters that we are expected to find, and then we were able to also give some analysis to our solution. All right, let's move on. Here is another question that we can easily look at. You can see that we have a diagram. We have a diagram, and we're expected to understand and analyze this diagram, and then from there we should try to find some parameters. We have a surface. This is an inclined plane. As you can see in this diagram, this is an inclined plane, and the plane is inclined at an angle of 20 degrees. And on this inclined plane, we have a cubic block. Between the cubic block and this inclined plane, we have a liquid. okay, and that liquid is oil. We have oil right in between here. Now, this cubic block is going to slide down, and as it slides down, it simply means that the shear force is going to be towards the direction that the cubic block slides. All right. Again, direction of motion, like I mentioned, is downward. So the shear force will be downward. And the shear force is parallel to the fluid motion. Okay? From the question, it is given that the film thickness, the thickness of oil is given as 0.03 millimeters, and that would represent our H. This is given in the question. I'm actually reading the question out to you. This is the question. So this is given in the question. Then mass of the block is also given in the question as 25 kilogram. And the viscosity of the oil is also given as 0.2 kilogram per meters per second. Also, we have to pay attention to the fact that this value of H is small. So we're dealing with linear velocity profile. That's what we're going to assume we're dealing with. What else do we have here in this question? We have our cube here. So finding the area of this cube is not going to be difficult at all. It's just going to be length times breadth. That's 0.2 times 0.2, because each of the sides that's given is, for the cube, each of the sides is given as 0.2. Each of the length is given as 0.2. And for a cube, all of these sides are equal. So the contact area of the cube with the liquid will just be the base, which is 0.2 multiplied by 0.2, and that gives us 0.04 squared meters. We also keep that somewhere. I think we have dealt with all the parameters on this particular slide that represents the question, and we have moved a step further to try to solve this particular problem. Okay, so to try to provide additional analysis by finding A. This is the only thing not given to us in the question. Every other thing you see here is given in the question except for this A that we just calculated, the area. All right, so let's move on. So we are supposed to find the constant velocity. This slide is not clear. Let's manage it. We have to use it like this. Sorry about that. Find the constant velocity of the block. We know that it's a Newtonian fluid, n is equal to 1, no doubt about that. So how do we find the velocity? This is our equation right from the beginning. The shear stress on the block will be equal to the minus viscosity multiplied by dv over y raised to power 1. 1 here represents our n, and this is Newtonian, like we mentioned in the previous videos that we dealt with. Okay, so we are dealing with the linear profile. This simply means that we can represent this with limit with delta v, delta y. As delta y tends to 0, this negative becomes insignificant because it represents just the resistance. And then we have shear stress is also equal to force over area. So we have force over area, which is shear force over area, will be equal to the viscosity of oil. This time around with no minus because the limit has come into play. We have delta v over delta y, where delta y is also equal to h. So we have this expression here because we're dealing with a linear profile. We are dealing with a linear velocity profile with resistance. All right, so we move on with this particular expression. So that is still the expression right up here. We have found the area. We have been given viscosity of oil in the question. We have found the area in the first slide where we read the question out. And then the velocity of the block. The velocity of the block VB is not known. The height is known. We're given that in the question too. So Fs is not known. VB is not known. But we can find our Fs with the parameters that have been given to us. When we observe this particular question properly, what you will notice here is that there will be a force of gravity acting on this block, and that force of gravity is Fg. All right, or you can just call it the weight of the block. The block is going to have horizontal force and vertical force acting on it. So the horizontal force is going to be the F shear that you can see here. When you find the horizontal force acting on it, it gives you a particular expression. How do you find the horizontal force? For some of you who did physics with me back in the years, some of the lessons of the physics are also on my channel. If you flip through, you will find the videos there on how you can find the horizontal component of forces and how you can find the vertical component of forces given the magnitude. So So the horizontal component is going to be equal to, if you're using cos, the horizontal component Fs will be equal to the magnitude of the force multiplied by cos of the angle that we are dealing with. Okay, Fs will be equal to Fg cos 70. Fs will be equal to Fg cos 70. Okay, so that's exactly what we have here. Fs will be equal to Fg cos 70. Our Fg is going to be the mass of the cubic block multiplied by acceleration due to gravity. That's going to be our Fg. So you replace Fg with mass times acceleration of gravity cos 70. If you expand that out, we know the mass is 205. We know the gravity is 9.8. Cos 70, we can always find that our 4-figure tables or calculators. If you multiply these out, you will find the shear force to be equal to 83.85 newtons. Okay, so once you find this force, the next thing you want to do is to bring it right up here. You bring your force right up here where you have Fs. This tells us that the only unknown we have in this equation is now Vb. And then we can go ahead and find Vb since we know every other thing. If you rearrange and mathematically solve this, you find your Vb to be equal to 0.31 meters per second. And this is exactly what they asked us to find. Find the constant velocity Vb of the block. That's what they asked us to find, and that's exactly what we have obtained here as 0.31 meters per second. All right. Again, we have dealt with a couple of examples, and I know these examples are examples that you can easily handle if you go over, this explanation again and again and again. Before you know it, it becomes a part of you, and you can easily deal with them without any pressures. Let's move on. There is another question here I want us to quickly evaluate together. This question has to do with rotational motion of a shaft. It's a very important part of our studies, and I want you to pay attention to it. There is an example here that I'm going to use to explain how this analysis is made, and I believe this will help you a lot. A shaft of 100 millimeters diameter rotates at 120 radians per second. You can always convert radians per second to meters per second. I'm going to show you how as we move on. Radians per second will mean angular velocity, so you can always convert it to linear velocity, and I'm going to show you how very soon. A shaft of 100 millimeters diameter rotates at 120 radians per second in a bearing of 150 millimeter long. The radial clearance, which is our h, by the way, is 0.2 millimeters, and the dynamic viscosity of the lubricant is 0.2 kilogram per meter per second. Derive a formula for the power loss, and then determine the power loss and then the torque produced. We're going to find many more things as usual, okay? And I want you to pay attention to the methods and the concept via which we find those parameters. Okay, so we can easily draw up what we have here. Don't forget we have a shaft that has a diameter of 100. And it is put in a bearing of 150 millimeter long. This is what we have here. You can see the length of the bearing as 150 millimeter long. You can see the shaft right in the bearing. Okay, and then this shaft has a diameter of 100 millimeters as given in the question. So this circle you see here is what you see here. The cross-sectional circle right on top here is what you see here. So you can see we have diameter of di because it is inside. This is the inside surface. Okay, so we have di, and then we can easily find our ri, which is going to be di over 2. We have the lubricant here, okay, and then you have d naught, okay, which is going to be the diameter of the entire cylinder. Okay, we have d naught to be the diameter of the entire cylinder. From the question, they give us the viscosity, the dynamic or absolute viscosity. They mean the same thing, which gives us 0.2 kilogram per meters per second. We also have our h from the question, given as 0.2 millimeters, which is 0.2 times 10 raised to the power minus 3, or 2 times 10 raised to the power minus 4 meters. The rotational speed is given as 120 radians per second, W, and you do know that our W is the angular velocity, which is given as 220 radians per second. So find the linear velocity. That's the first thing you want to do. The linear velocity will be equal to the angular velocity multiplied by the radius of the shaft given to us. The radius of the shaft is going to be 0.05 because the diameter of the shaft in the question is given as 100 millimeters. The radius will therefore be equal to 100 over 2, and that gives us 50 millimeters. To find the radius in meters, it becomes 50 millimeters divided by 1000. If you do that, you would obtain 0.05 as the radius. Okay, multiplied by 120 radians per second, that would give us 6 meters per second. So this is going to be our linear velocity. All right, you keep that somewhere. Then secondly, you want to find the contact area. Finding the contact area with the fluid is not going to be a big deal because we know that the area will be equal to 2 pi RL for the shaft, the cylindrical shaft. And we know our R is equal to D over 2. 2's will cancel out. So you're left with area equal to pi DL. We know our diameter to be 100, and then we know the length also to be 150 millimeters. So if you convert 100 millimeters to meters, it gives us 0.1. If you convert the length, which is 150 millimeters to meters, it gives us 0.15. So the area will be pi multiplied by 0.1 multiplied by 0.15, and that gives us 0.04712 squared meters. Okay, so we found the area right now, and then we also found the linear velocity, and these two will be useful as we move on. Then the next thing you want to do is to find the resisting force. All right, the pipe is fixed. The velocity of the pipe is fixed, okay, because the shaft is actually in the pipe. So the shaft is moving, the shaft is in motion, but then the pipe or the bearing is not in motion. So the velocity of the pipe is fixed. So it's going to be equal to 0. And we do know that our shear force over area equal to viscosity multiplied by delta V over H, which is equal to viscosity multiplied by delta V will be V shaft minus V pipe, which is V shaft is the velocity, the variable velocity at the top minus velocity at the bottom, which is a fixed velocity. So that's why we have V shaft minus V pipe over H. V pipe is 0, okay, because it is fixed. And then we have our H here representing our delta Y, by the way. So you all know how we got here in the first place. And with all of these, we can have our Fs over A is equal to viscosity V shaft over H. Okay, we know our viscosity is equal to 0.2. We know that. We found our area to be 0.04712. We calculated that too in the previous slide. And then we know that our V shaft, we calculated that too. That's the linear velocity is 6. And then we know our H is given in the question as 0.2 times 10 raised to the power minus 3. If you put all of those right in the equation, we can easily find our S by just cross multiplying, and then the A comes here. If you do that, our shear force will be equal to 282.72 newtons. Okay, so we found the shear force. Then the next thing is to find the torque. What is the torque? The torque represents the rotational force. Okay, it's a force of rotation. That's what a torque represents. Okay, so it is usually given as a rotational force. So the torque will therefore be equal to the force applied multiplied by the rotating arm. The force applied, we calculated that to be 282.7. The radius will be equal to 0.05. So what we should have right in here should be 0.05, not 0.015. All right, so this should be 0.05. You can want to change that. Okay, multiplied by 282.7, and that gives us 4.24 Newton meters if you multiply that out. So once you have the torque as 4.24 newtons, the power, we know right from time that power is equal to work done over time. Work done is equal to force times distance. So power is equal to work done over time, which will be equal to force times distance over time, which therefore be equal to force times velocity, because velocity is equal to distance over time. So we have force times velocity as power. Now, the power needed will therefore be equal to area multiplied by viscosity multiplied by Vs over H multiplied by this Vs. Now, this Vs you see here is this V that you can see right here. This is V. So this F that you see here is what all of these represent. Okay, you know that we had said earlier that force over area is equal to mu Vs over H. Okay, force over area is equal to mu multiplied by velocity over H. So if you cross multiply, it means force will therefore be equal to A multiplied by the mu, which is the viscosity, multiplied by Vs H, and then we still have our, our velocity of the shaft. We still have it here. Okay, power will therefore be equal to this force, all of these values, multiplied by this velocity that we do have here. We were asked actually to derive an expression for the power. This is the expression they asked us to derive. If you go ahead, we know our A to be pi dl. We know our A is going to be pi dl multiplied by mu multiplied by Vs squared over H. This then becomes the power expression that we've been asked to develop, this one. Okay, and with all of this, everything becomes easy. We know H, we know mu, we know our H, we know our viscosity, we know the length, we know the diameter, we know our pi, it's a constant, and then we know our Vs because we calculated the Vs. If we put all of those in here, we can easily find the value of the power, and then that gives us about 1696.2 watts. When you put all of those values right in there, you obtain 1696.2 watts. All right. So this brings us to the end of this particular example, and we've been able to find all the parameters that they asked us to find. Go over these lessons again and again and again. Go through the lecture notes too that will be made available to you, and at the same time, try to understand everything that seems suspicious to you. If you have any questions along the line, feel free to ask me, feel free to reach out to me. I will try to assist you in whatever way I can, All right, this will be the end of this lesson. Go ahead and subscribe to this channel, give this video a thumbs up, and as much as possible, I'd like to read what you think about the method of delivery of this teaching, the concept that have been shared, and let me know if you love it, if you like it. Just put a comment in the section. I'd love to read from you. I'd love you to really be a part of the community that we're building here. Thank you very much. See you in the next lesson. Bye.